This next example, we're going to take a look at sizing a motor. So we're going to situation where we've got some fluid power available and I want to be able to accomplish some type of work. And this is actually a real example that we were working through a couple years ago. We were developing a harvester that would harvest hemp, and we were looking at different power supplies. We ended up actually using electric power on the thing, but we were experimenting with fluid power at some point. And so we're looking at a situation where a tractor, an agricultural tractor, develops some fluid power out of the back. And we're going to test this in lab. And so there's outlets that we can plug into that'll give us a certain amount of power available. And so for the tractor that we were working with, so here's the example. So the tractor that we had would develop 95 liters per minute. So we tested that or looked at the specification for the tractor, and it would develop 95 liters per minute. And it also said on the specifications for the tractor that its pressure was 18 megapascals. So that's what I've got available for fluid power, 95 liters per minute at 18 megapascals. Now, what do I need? So in this particular application, we were running a cutter bar that was going to cut the hemp plants. And so what I needed on the output, my mechanical power, was 3.7 kilowatts. 3.7 kilowatts of power, and it was going to have to rotate at 280 RPM, which is relatively slow for a hydraulic motor. So 280 RPM at that speed. So how do we do this? So let me get a different pen here. And let's see. So we got motor size. So that's what I want to know. I want to find out the motor size. What do I need? How big of a motor will do this job with that much available? Okay, so a couple things I'm going to have to look at, and this is going to be interesting. Let me throw out here just some givens so that we can work with that, and then say for the motors that we buy, the supplier, I looked at our supplier. Typically when you buy a new motor from this company, their volumetric efficiency is 0.96, and the torque efficiency from the company we were looking at was about 0.98. So there's some numbers that we can work with. Okay, so motor size, how big of a motor? Now there's actually two different things that I've got to look at here. Okay, so I need to develop a certain speed, and I need to develop a certain amount of power, or analogous to that, a certain amount of torque at that speed. So I have a certain amount of power that I need to develop a certain amount of speed. So think about motor size a little bit. And let's just, before we put equations down, let's just think through this. So if I have a certain flow rate and I run that through a motor, the motor is going to run at a certain speed. If I have a bigger motor, does it run slower or faster? Well, a bigger motor, larger displacement, and it's going to take more material, it's going to take more fluid to make that motor rotate one revolution. So the bigger motor is going to run slower. All right, so what that tells me, if I need to develop 280 RPMs, then my motor is too big, that 95 liters per minute is not going to develop enough speed. Okay? If it gets too small, it's going to run too fast. But what I can do on a tractor is I can regulate this flow rate. This is the maximum available. The 95 liters per minute is the maximum available. So I can regulate, put a valve in there or some type, and we'll talk about volume control valves, and I can slow it down, limit the amount of flow that's coming out of that, and that's going to control this speed. So what that tells me is, hey, the maximum, I can find out a maximum size of the motor based on how fast it's going to need to run. All right, so let's go ahead and do that first. So let's figure out the maximum size of that motor. So we can do that, motor size, and you can go back to those equations, and I'll let you look at your slide and figure them out. But again, we got to watch on motors. The displacement of the motor is the flow rate divided by N. And again, motors are opposite from pumps, and so the efficiency goes in the other place. And when we were working with a pump, we put the efficiency in the numerator. We're actually going to put the efficiency, the volumetric efficiency, in the denominator now. So that's going to tell me the size that I need, the volume, the displacement of the pump. Okay, so let's figure this out. Let's run through it. So, and what are my units? Before I go, I'm going to need cc's, cubic centimeters, and I'll write it this way just to be different, cubic centimeters per revolution. That's what the units are, again, even though we sometimes just say cubic centimeters for that. All right, plug it in. So flow rate is 95 liters per minute. Speed that I need the thing to rotate is 280 revolutions per minute. Look at that. The minutes cancel off. The revolutions are in the denominator where I want them. I got to put my efficiency in there so I don't forget it. So my efficiency is, volumetric efficiency is 0.96. So it's 1 over 0.96. And let's see, I got my units there, so the minutes are gone. I have liters per revolution. I need to get the liters to cc's, so that's times 1,000 cubic centimeters per revolution, like that. And now I can just, excuse me, cubic centimeters, not per revolution. That is cubic centimeters per liter. I'm sorry, so that cancels the liters off. And I end up with, what does that tell me? 353 cubic centimeters. So that's the biggest motor I can have. If I go any bigger than that, then my 95 liters per minute is not going to make it run at 280 RPMs. It's going to run slower, and so I need it to run faster. So that's as big as I can go, all right? So that's one limit of that. But now let's look at the torque. Let's think about this torque side of this. I have to develop so much torque. So what does motor size have to do with that? So I could go, again, I could go smaller, so I don't have to buy, this is a really big motor, 353 cubic centimeters is a really, really big one. So it would be a whole lot cheaper to buy a smaller one. And then I just regulate that flow rate, put a valve in there so that the motor doesn't spin too fast. So the tractor has more available than I can use. So I can do that. So there's that 353 cubic centimeters. But what's the trade-off now with torque? So how do I develop torque? I develop torque based on, what is my torque equation? Let's go ahead and write that one down. So my torque equation is, let's see, the torque equation is the size of the motor is torque about, well, let me back off. Torque, yeah, let me back off, do something a little bit different here. So I want to explain something before we get to that point. So let's, again, thinking about this torque. So torque is going to be, you develop your torque based on the amount of pressure that you have. So the pressure and torque are related by the size of the motor. Okay, so the bigger motor at a certain pressure is going to develop more torque. So if I go a smaller motor because I don't want to buy this really big one and I want to control the flow rate down, the question is, do I have enough pressure available to develop the torque? So there's going to be a minimum that 18 megapascals is going to say, you know, if I got 18 megapascals, I can't go any smaller than a certain size, or I'm not going to be able to develop the amount of torque that I need to develop. Okay, so we got to find the minimum size based on that. So let's look at, and I need torque, so let me go ahead and calculate torque. I have power up there. So I said that I need 3.7 kilowatts. So let's calculate how much torque that actually is that I need to develop. So torque is power divided by speed. And let's see, the power that I said is 3.7 kilowatts. So let's make this 3,700 newtons meters. A watt is a newton meter per second. So 3.7 kilowatts is 3,700 newton meters per second. That's my power there. My speed in the denominator is, what did I say up here, 280 revolutions per minute. All right, so torque I need in newton meters. So I've got minutes and seconds here, so let's get rid of those. So 60 seconds per minute. That's going to get rid of that. Now, that gets rid of the minutes, gets rid of the seconds. I have newton meter in the denominator, but I got revolution in the numerator. And here's where we got to be careful of those magical units constants. We got to watch through the units what I need. I need torque in newton meters. I've got to get rid of this revolution in the bottom here. All right, so I need to say that there's 2 pi radians, or actually I need to put the 2 pi in the denominator. So 2 pi radians per revolution. That puts the revolution in the numerator. I cancel the revolution off. The 2 pi is considered to be unitless, and so this tells me that I need 126 Newton meters. That's the torque that I need to be able to develop, okay, by that motor. All right, key is, again, watch this 2 pi. And this can get confusing because when we're talking about displacement up here, we need the revolution. So the revolution is part of that displacement unit. But when we're talking about torque and other things, we got to get rid of it. So you got to really pay attention. Do I need the revolutions in there or not? And be careful what we do with that, okay? So that's what you have to watch. Okay, so now let's calculate our displacement. So this is going to be the minimum. I can't go any smaller than this. This is going to be based on the pressure available and the amount of torque that I need to develop. So the displacement of my motor is going to be equal to the torque divided by the pressure. And again, motors are opposite than pumps. The torque efficiency has got to go in the denominator here to make that happen. All right, so let's run this out. Find out again what we're after here in units. We're after cc's per revolution. That's the units that I ultimately want. So torque, what's my torque? I need to develop 126 Newton meters. All right, and that's over 1. Let's see, delta P, the pressure, is 18 megapascals, so I'll say 18 times 10 to the 6th newtons. Pascal is a newton per square meter, so I'll break that down in newton per square meter that we have up there. Oh, look what I got in the numerator already. A square meter there, so that's a cubic length. So hey, there's probably my displacement. Newtons are canceling out. Oh man, I'm about done, aren't I? Don't forget the efficiency. So the torque efficiency is 0.98. So I have 1 over 0.98. And let's see, do I need anything else? I think that's it, right? So I got 1,000, let's see, 1,000, I got to get the cubic meters. So I have 1,000 squared cubic meters, or cubic centimeters per cubic meter. So that gets rid of that cubic meter, gets rid of these two and that one, and I'm left with cubic centimeters. Oh, that's what I need, cubic centimeters. Oh, I need cubic centimeters per revolution. Here we go, watch the units. And that's why I put it out there to remember that, hey, I need to have cubic centimeters per revolution out here. So I need to put my 2 pi in there. So I need to have the, let's see, is it good numerator? I need the revolution in the denominator. So I need to put the 2 pi in the numerator. So that gives me cc's per revolution. Here's the key, folks. Be careful about that because don't forget that units conversion in there. Sometimes we need the 2 pi and sometimes we don't. Watch the units carefully, okay? In those magical units constants and those equations, that stuff is all built in and you forget about why do I really need a 2 pi? Is it in there? What's going on there? So I want you to be able to think through that, look at your units carefully and understand how to make that happen. So what this tells me, if I hammer this out, that tells me that I need a 44.9 cc or centimeter cubed, however you want to write it. Again, I'll just put the centimeter cube because we imply that the revolutions go with it. So here we go. I got the 2 limits. So based on the amount of pressure available and how much torque I need to develop here with the power and the speed, that tells me that I can't go any smaller than 44.9 cubic centimeters. All right, for the speed, I can't go any bigger than 353. So, you're an engineer, what are you going to pick? And here's where I could just pick anything in the middle. Should work, it should function correctly, should. All right, I'm going to talk about that in just a second. So I'm going to pick something. There may be a lot of factors that go into that. I might go back to some of those efficiency curves and see if I pick something closer to the 44.9 or closer to 353, how would it operate? What would it be, its efficiency be? The other thing to think about is a really, really big motor is going to be really, really expensive. So one more this size is going to be a whole lot cheaper. And so cost might come into play there as well. And so, again, anything between those is going to work. As an engineer, I just have to pick something to make it happen. But now we've got to be real careful about this. We're going to hit this more as we talk about performance of valves and things like that. But we're going to look at performance curves of the hydraulic system. You're going to get these in the lab. We're actually going to calculate these things. And we're going to calculate or measure the flow versus the pressure available, flow versus the delta P for a system, okay? Now, what I told you on the tractor, hey, we have 95 liters per minute available, and we have a pressure of 18 megapascals. And I wasn't very explicit about that, and I kind of did that on purpose, because a lot of times we'll see those kind of numbers in specifications, and what do those numbers really mean, okay? Because oftentimes that 95 liters per minute is the maximum flow rate. So that 95 liters per minute is up here, maximum flow rate, which is going to occur when I have a pretty low pressure, when there's not much resistance to pressure. So as I have a higher and higher pressure, so as I have resistance to that flow rate, I'd like to see that performance come out here really, really square, but really what I'm going to see is that thing drop off, all right? So it's going to start to drop. So when I get at a higher pressure and working at higher and higher pressures, I'm going to have lower and lower flows available. So that's one of the things that I have to be careful of, all right? The other thing is, look at that 18 megapascals. That's probably telling me that that's my maximum. Well, at that maximum pressure available, I'm basically going to have zero flow. So we're going to see that we actually get a performance curve that looks something like this, okay? So we've got that curve that rolls off like that. So at this maximum pressure, I have zero flow rate. At the maximum flow rate, I have zero pressure. So if I need pressure and flow to have power available, it's got to be somewhere in between. Okay, so I can't get both at the same time. So I looked at these numbers out on the edge, and if I needed, if these numbers are really close together, that's going to tell me that I need to be operating up pretty close to this point up here. I can't get up there, okay? The maximum I can get is somewhere down in here. So there's going to be a disconnect or a distance between what the theoretical maximum is based on these limits and what can actually happen in here. So that's the other thing I got to be careful of, is whatever I pick, make sure it's inside this curve somewhere. And again, I can operate inside the curve. Unlike an engine where I'm kind of stuck on the outside of the curve there, I can operate down here just by saying I'm going to limit flow rate. So I'm going to say, okay, I'm going to put a flow meter, flow control valve in there or something, and I'm going to limit the flow to this speed, okay? And so that'll allow me to operate anywhere on that curve until I come up and hit this outside curve where it starts to roll off. So that gives me a lot of operating envelope in there. So that's just the other thing that I would have to be careful of with these two numbers, or whatever I pick, that it's down inside the real performance curve, so that I can achieve the conditions from the output of that tractor. So that's how you pick it out. That's some of the design. You see a lot of the factors in there. Again, watch the units. Be careful with the revolutions. Sometimes we need to put it in there and sometimes we don't. So watch the units pretty carefully on that. And think like engineers. Where are you going to design this? Where's the most efficient point? And so forth.